Hi everyone. This lesson is going to be about the topic proof by mathematical induction, which is a very powerful and important technique which we use to prove conjectures. So here is an example. Use the method of mathematical induction to prove the following. Let's break this down a bit. Pn stands for a proposition. A proposition in mathematics is an idea, a conjecture, something which is, we think, we're pretty confident that it's true, but we haven't proved it yet. And the proposition is that the sum of the odd numbers, the positive odd numbers, up to some finishing point, equals n squared. And as long as n is a positive integer, now that symbol there's a little bit wrong. That symbol should have been an element of. N is an element of the positive integers. That's probably a typo. Now, where would a mathematician get this idea? Well, they might have got the idea from a picture. They might have been doodling like this. In this first case, if I say for this one n equals 1, then the odd number 1 adds squared is 1, and it's 1 square unit. In the second case, if I say the edge of this second square here is 2 up to there and 2 to there, so 2 squared is 4, and it certainly would be 1 plus 3 if we added 3 there. If I consider the next one, I think you get the idea. If I go, why won't that rub out? There we go. If I go from there across to there, so the third case, and from there up to there, the third case, 3's are 9, and if I add 1, 3, and if I add this bit, which is 5 squares, 1 plus 3 plus 5 is 9. Now, it certainly seems like it's going to work. If we keep adding the odd integers, positive odd integers, we get a square number. So let's see if we can prove this formally. So let's write the required to prove statement a little bit more neatly. So it's a proposition with n as a value, so it could be for 1, n equals 2, 3, like I was saying. And what is our proposition? When I have something like this, a great big list of things added together, it's more compact if we use sigma notation, and we'll use a counter or an increment variable, I. So I will go from 1 to n, and the expression at the end there, if we write 2i minus 1, now that's going to give us the exact thing that I've highlighted in yellow. If we substitute I equals 1, then 2, then 3, all the way up to I equals n, it'll be exactly that. And we're saying that that's equal to n squared. That's our required to prove. The first thing we do is we consider the base case. So we let n equal 1. And then we consider the proposition with n equals 1. Now the left-hand side of that proposition would literally be the sum from I equals 1 to 1. So n is the upper limit of 2i take 1. Now if we substitute 1 into there, we'll have 2 times 1 is 2 minus 1. We don't have to go any further because the beginning value is 1 and the upper limit is 1. And 2 take 1 is 1. The right-hand side of the proposition was n squared. So I'll write n squared. And of course, we're looking at n being 1, and 1 squared equals 1. So we can confidently say that the proposition 1 is true. We have tested the left and the right-hand side independently, and we have a true statement. That's the first step, or the base step, in proof by induction, testing the first case explicitly. Now, the next step is to assume this is true. Seems odd, but I'll get to that why. We will assume that the proposition is true for some value k. And k, of course, would also have to be an element of the positive integers. And k could be 1, but it's probably more than 1. K is some positive number. Now, I will write this explicitly. In other words, the proposition would be sum from I equals 1 to k of 2i take 1 equals k squared. And I will need to refer back to that, so I'll put a little note there. This is an assumption. We are basically writing the proposition, so there's my original proposition in terms of n, but I'm writing it in terms of a different pronumeral k, and I'm assuming it works. I'm fairly confident it works. So now this is the clincher. We have to consider the next case, proposition k plus 1. It's got to be always k plus 1, not further. So what would that look like? In other words, we are required to prove that the sum from I equals 1 up to an upper limit of k plus 1 this time of 2i take 1 equals k plus 1 squared. So we have to prove that. And we will start with the left-hand side, which equals sum from I equal 1. Now, I know you're going to think that I missed one there, but I didn't. Because if I'm summing a list of items all the way to the element k plus 1, I would first have to sum the first list of elements up to element k, then add on the last one. So the left-hand side, it's quite subtle, but k plus 1, adding a list of elements up to k plus 1, I have to add the previous list and then add on the very last element, the element k plus 1. Now that's a bit of a boo-boo. I jumped in too quickly there. I have to imagine substituting k plus 1 into this expression, because k plus 1 is a value, the terminal, the last value of I. So that was a close call. 2. Now, instead of I, I'll put, sorry, getting myself bent out of shape there, k plus 1, and then subtract 1. So that's the last term in our expression where the final value is k plus 1. Now, here's the inductive, or the use of the assumption. We made the assumption that this expression equals k squared. And that's exactly the expression we have here. Make that small enough to see. So we can replace sigma I equals 1 to k of 2i take 1 with k squared. Now we're assuming it's true, aren't we? So we're allowed to work with that. We can put all of that equals to k squared, and then expanding to make this easier would be 2k plus 2 take 1. And I will make a note here that this was by assumption 1. So we had stated the assumption, we're using the assumption. We will always make use of the assumption. So that's k squared plus 2k plus 1. That's a quadratic. It's an easy quadratic, and it would be a perfect square. It would be k plus 1 squared. Now, if we look back for a minute at what we were required to prove, we were required to prove that this thing equaled k plus 1 squared. That's where we're at. We have got to the point where we can say right-hand side. So it's subtle, and it takes a little while to get your head around it, but we've done enough to show that this thing is true. Let's recap. What did we do? We first did the base case. We let n equal 1, and we showed that the proposition was true in the case when n equaled 1. No doubt there. Then we assumed that the proposition was true for some value k, and on the basis of that assumption, we have showed that the next one is true. So that means we know that proposition 1 is true, so it follows that proposition 2 must be true. And if we know that proposition 2 is true, it follows that proposition 3 must be true. And if proposition 3 is true, it follows that proposition 4 must be true, and so on forever. That's what we call mathematical induction. So we will say, therefore, if proposition K is true, then proposition K plus 1 is true. That's what we showed. As proposition 1 is true, we also showed the base case, then by induction, proposition n is true for all numbers n which are elements of the positive integers. Q, E, D. And we're done. Proof by mathematical induction is a very important topic in mathematics, and it takes quite a while to get accustomed to the logic behind the proof. But the proofs all have the same pattern. They will have a proposition, there will be a base case, usually when n equals 1. Then we will make an assumption that the proposition is true for some value k. We will use that assumption to prove necessarily that the following case is also true, that proposition k plus 1 is true. And that's enough. It's enough then to say that proposition 1 is true, so it follows that proposition 2 must be true. If 2 is true, then proposition 3 must be true, and so on forever. It is vitally important that you practice these. You will not master this by watching a 12-minute video that I've made. You will need to practice them for yourself and struggle, and you'll make mistakes, and then you'll go back and you'll get some help from your teacher and you'll fix your mistakes, and that's what learning is. You must put in the effort, and this is a difficult idea to get your head around at the beginning, but once you do, it is very powerful and it is very important in higher mathematics. Thanks for watching.